So let's get started. So today the lecture is going to be the last part of gradient descent, and so in particular, what we're going to talk about how to use the techniques we learned about the last two lectures to actually fit when your function that you're trying to optimize is derived from data, and particularly is going to be a quadratic loss function, like the sum of the squared errors, then it's going to discuss how to use gradient descent inside this context. All right, and so this is going to kind of tie everything together. We're going to look at a problem from like the regression section and solve this with gradient descent. And actually, this is the most common way it's solved. You often add these other regularizer terms that means that you might not have a closed form solution like we saw before, but you can still use gradient descent. And there's going to be a couple of pieces of nice structure that pop out that's going to be consistent across most of data analysis. So we're going to not only go through this kind of extended example, but also identify some key structure here. So, okay, so just looking at the schedule, as we usually do, start of class, we're the last lecture in gradient descent. This will conclude what quiz number 4 is going to be on. Quiz number 4 will just be on the last 3 lectures in gradient descent. So the previous 2 lectures and so this lecture. And that's going to be after class or the end of class on Monday as well. And it's this same drill as before. You're going to get one sheet of a cheat sheet. I strongly encourage you all to make. I think it's a good studying technique. And if you turn that in, you'll get 5 points towards your grade, although that could be bonus, but can't exceed 100% on that. And then homework 3 is out, and hopefully you start working on that. That's going to be some parts of linear regression and some parts of gradient descent. In particular, question 3 is a gradient descent question, and I intend that you start with this code from Colab that we looked at in the last lecture. This gave this example where we're kind of plotting this 2-dimensional function and we're taking these steps. I want you to recreate this. There are 2 functions I want you to do this with. One should be easy, one should be more challenging. In both cases, you're going to have to play with some of the plotting parameters to understand what's going on. This is a great tool to understand what's going on, and I think it's helpful to understand. And again, the plotting will help you determine if you have to take the derivatives yourself to create the gradient function to check whether that makes sense. Okay, if you zoom in far enough, it should be consistently going downhill. Okay, that's how you check whether your gradient calculation is correct, because you're going to have to write that they're polynomials, but maybe you're a little bit rusty of taking these partial derivatives. You have to do an expansion and all of this. It's not too hard, but it's easy to make mistakes. Plotting is how you check whether you're doing it correctly. Okay. So then we'll, and so that's about where we are in the schedule. And then next lecture, we'll start the dimensionality reduction section. And some of the discussion on eigenvalues and eigenvectors is kind of, is a warm up for this. We'll think of it that way. Okay. So we're talking about gradient descent and so fitting data onto the model. So now instead of starting with the function f, we're going to start by having a data set, and we'll call this again xy. This will be a supervised learning problem. So we have labeled data, right? So this will be the set x1, y1, x2, y2, up to xn, so yn. Okay, and each of these, and this, I guess, this will be a subset of our D cross R, right? So the data points are going to be in D dimensions and the label is going to be in 1 dimension. And our goal is going to be build a model. In this case, it's going to be the regression problem, right? So the goal is a model M alpha from some family of models. In this case, we'll say with some k parameters. If it's a, we'll focus on a polynomial example. That'll be simple, but it could be that alpha here is going to have k parameters, so it's up to alpha k. This may commonly be d plus 1. We'll look at a a quadratic polynomial, which will be k equals 3. In the main example we'll look through in class. Okay, and we want to find this model, so it's trying to optimize some sort of, or not just optimize, but so minimize a loss, so some sort of loss function, and this will be L. We'll write this as some loss being the accuracy between the data and the model that we find, and we want to optimize the choice of this model. Okay, and what we're going to do is we're going to turn this in, right, this into a function f of alpha. Okay, before we've looked at these functions, these prediction functions, which is what the model is doing, that takes in a value x. Right now we're taking this value alpha, right? So this f of alpha is going to be from Rk, the space of the model parameters, right? It's going to be parameters by some small number of scalars, a vector in Rk, and it's going to give us some sort of value here. Okay, and the goal is going to be then to choose, again, the alpha parameters, which minimize this loss function. And for regression before, we talked about how there was this kind of closed form solution, which depended on the inverse and some linear algebra. Now we're going to do this with gradient descent, and it will be particularly useful when this loss function is exactly the sum of the squared errors, right? Which we have talked about a lot of this in this class, and we'll keep talking about. Okay, and so this, just to recall, is going to be all these xi, yi in this data set, xy, right? The sum over all of these terms of yi minus the model m of alpha at xi squared. Okay, so this is a very common formulation, and this could be where the model is a linear regression model, but we'll see it could also be a clustering model, a dimensional reduction model, and in some cases a classification model. The approaches we'll focus on this class for clustering and classification will exactly be this model, this loss function, this function we're optimizing. Again, for classification, we'll start here. We'll show that it's not that there's some kind of issues with this version, and we'll kind of look at other sort of loss functions in this case. But again, we'll use gradient descent within the classification framework as one of the tools. It turns out for the special cases we look at in clustering and dimensional reduction, we'll actually need to do different algorithms because these are not going to be convex through some strange structural properties, but they work nonetheless because of some nice properties of sum of squared errors. Okay, but in general, this idea of having a sum of squared errors, defining a loss function which has a model parameters for optimizing is very common within machine learning and data analysis. Okay, and if you recall, part of this the sum of the squared errors you can derive from a Bayesian inference point of view where if you think about there's a model and then there's independent Gaussian noise on each of the points, and you want to find the maximum likelihood estimator, or actually the minimum of the negative log likelihood estimator, you can drive actual loss functions that look like this from the statistical perspective. Okay. So enough, hopefully you believe me that this is a reasonable thing to try and optimize at this point. Okay, so let's look in particular at a case now where we're going to have, again, our data xy, and x is going to be in Rn, and y is going to be in Rn also. So, okay, so we just now, every xi, so xi, yi is going to be an element of R cross R. That means x is one-dimensional in this setting. But the model what we're going to consider now is going to be so just as an example, it's going to be quadratic. Okay, and so that means we're going to have m of alpha of xi. We're going to write this as, I like to write as a dot product 1 xi squared. And if you remember, this corresponds with the model alpha 0 plus alpha 1 xi plus alpha 2 xi squared. Okay, so this allows us to fit a quadratic function for a quadratic regression model through a set of points. Okay, if we plug this into the sum of squared errors, this is exactly the quadratic, one-dimensional quadratic regression problem. Okay, I'm going to use this as the main running example. It's basically, I think, the simplest example that really demonstrates all of the complexity. You can instead, you can mentally in your mind as we're going through this, you can kind of replace this at, say, when there are multiple dimensions of these explanatory variables. Say if we had two-dimensional explanatory variables and the xi squared term, that's just the second kind of explanatory variable instead, right? Or if there's a cubic regression, you have another term here. Or you have three explanatory variables and it's linear, there's another term. Or if you have a quadratic on multiple explanatory variables, you just expand the polynomial and look at all the coefficients, okay? But it's going to have roughly this sort of structure here. Okay, so in general, I have this form, and I think this kind of will give you insight into what's going on here. But this is going to be, in principle, much more general. Okay, and so what we need to do is we're going to run gradient descent, right, on this f function, which is going to be sum equals I equals 1 to n of yi. I think I write this the other way around, just to be consistent. M of alpha xi minus yi squared, right? So this will be our overall function we're trying to optimize over alpha now, over the choice of alpha. And to run gradient descent, remember, it's just this one step where you update the old. This one is the old model parameter, and you're updating with the new parameter by having some learning rate times the gradient of the function x. And, just a reminder, this upside down triangle is, again, you can write this in LaTeX as as it's a Greek letter, something called a so-called a nabla, N-A-B-L-A. Okay. Now that's might be confusing if you haven't done before, but okay. And so in order to do this gradient descent now, we just need to be able to take this f function, and we need to be able to compute its gradient. Okay. And so, okay, so we're going to start this example with, we're going to start by looking at this, where let's look at a single data point. Okay, so we're going to have x, y is just going to be x1, y1, right? So in this case, n is equal to 1. Okay, so this is going to capture a lot of the complexity of what's going on. And then when we expand from n equals to 1 to n equals to a big number, we're going to actually see kind of, different ways you can do this. And these different ways are actually going to be kind of interesting and give us different algorithms. Okay, so let's focus on just the single data point. Okay, and then just to rewrite this here, f of alpha is going to be, I'll just denote this, we'll use this later. This is going to be f1 of alpha. Okay, it's just indicating it's the first data point. In this case, there's only one. So we'll just put this f1 of alpha here. They're equal. And this is going to be, I'll expand this out, alpha 0 plus alpha 1 x1 plus alpha 2 x1 squared minus y1 squared. Okay, so this function is going to be, this function is going to be, is going to be convex in this, in the choice of alpha. Okay, this is going to be convex in alpha. Okay, and I'll try and draw a picture of this later and hopefully convince you at that point, but it's going to be convex in alpha. Okay. Okay, so that means we should be able to run gradient descent here. Okay, so in order to compute the gradient, right? Remember, we need to remember that the gradient of alpha is going to be d alpha 0 of f alpha, the partial derivative with respect to alpha 1, f of alpha, and the partial derivative of alpha 2 of f alpha. Okay, so if we want to compute the gradient, that's the one term we need in order to run gradient descent. Assume we know the learning rate, or we can do one of these backtracking line search techniques to start big and then adjust it down so it converges well. Okay, so then all we need to know is be able to calculate this derivative. This is the key step here. Okay, and so then let's actually go and calculate this derivative, or this partial derivative here. So I'll use alpha j. It's going to be symmetric for all j. Okay, of f of alpha. Okay, so this is going to be d of alpha j. Let's just write this out as m alpha at x1 minus y1 squared. Okay, right? So this is, and so I'm not going to use the full expansion right away. What I'm going to do is this kind of this product rule, and I can say that this is going to be equal to 2 because I'm doing this. I think of this as a product of this term twice of m alpha x1 minus y1 times d alpha j m alpha x1 minus y1. Okay, so I've gotten rid of the squared part now, right? I've done the product rule over this m, m alpha of x1 minus y1 times itself, right? So, or you can think of just kind of this function rule, you know, whichever way you want to derive this. And there's this 2 out front, right? In some cases, actually, this 2 is going to stay up front the whole time we do this as a coefficient. Sometimes I'll write the sum of the squared errors with the 1/2 in front because they really care about the derivative and they don't want to carry this 2 around all the time, okay? But there's this kind of, this 2 out here, which is a constant factor. You can ignore it, absorb it in the learning rate, anything you want to do. Okay. Okay, so let's kind of, now I can do this 2 m alpha x1 minus y1, and we need to take this derivative, and now I'm going to replace, I'm going to expand out this model, right? I can write out this model now as j equals 0. I should use j twice here. Let's do I here up to 2, okay, of alpha I x1 to the power I. Remember, anything to the power 0 is 1, so that's how we get the constant term minus y1 here. Okay. And so now this is easy to take the derivative. I've got these 3 terms here, but in general, I could have more terms. Whenever I have a polynomial thing, I expand it into some number of terms. But the only terms which are interesting are the ones where it's with respect to alpha j and they're alpha I here, right? Those, I have 3 terms, but each term only has 1 index I, and only when I and j match is this actually interesting. Okay, so I can pull this down, m alpha x1 minus y1, and then I can take this derivative with respect to alpha j, and the only term that remains is going to be x1 to the power j. There were 3 terms here, but only 1 is left over. Okay, so this is actually nice. I can do this symmetrically for each of the values j, each of the 3 terms here, and I'm always going to get, I can always break it down into this factor, which is going to be there for all of them, the 2 minus the residual, and then this other factor, which is kind of for this alpha j, it's going to be actually the coordinate value at that corresponding, that data point, maybe to the power j, right? But the j coordinate effectively of that data point starting from 0. Okay. Okay, now if we put this back together, right? So we can write out that f of alpha, so the whole gradient now, remember, is going to be d of alpha 0, f of alpha, d of the partial derivative with respect to alpha 1, f of alpha, and the partial derivative with respect to alpha 2, f of alpha, right? And so this is going to be exactly equal to 2 times m alpha x1 minus y1. So this is the residual times a vector, which in this case is going to be 1 x1 to the power 1 and x1 squared. Okay, so it's always, for any sort of polynomial regression formulation, it's always going to take this form where it's 2 times this residual, right? It's going to be 2 times this residual, and then multiplied by a vector, right? So the yellow term is a scalar, right? And then the blue term is going to be a vector of the coordinate values at that spot. So I'm basically the derivative tells me I'm either moving, depending on the sign of the yellow part, right? That could be negative or positive. I'm either moving towards that data point or I'm moving away from that data point with my model. That's what it's saying. And the magnitude of that step is going to be based on the size of the residual, right? So this is called the either the LMS for least mean squares, so update rule, or this is sometimes called the Widrow-Huff learning rule. Okay, so this comes up a lot. It's named various ways, but whenever you have a least mean squares where you're trying to minimize the sum of the squared errors, then the update steps are going to look like this. This is for a single data point. Okay, so if we have a lot of error, we're going to take a big step. The yellow term is going to be big. If we have a small amount of error, we're going to take a small step. Okay, and when we put these together, the data points which are not matched very well by the model, those are going to have a big residual. Those are going to have weight highly in the gradient. The ones which are going to be matched well by the residual, those are not going to affect the gradient very much, right? Until things are kind of evened out. Okay, and hopefully they're all small if your model fits the data pretty well. Yes. So okay, so basically all sum of squared error models are going to look something like this. The case of the derivative is going to be slightly different. I'm going to need we'll have to drive kind of something like this in this case, but it's going to look sort of like this way. So I think you're going to do something like this for the next homework, for homework 4, which is not posted yet. Okay, so you'll end up working through, you'll start with the regression problem, you'll take the gradient, which will look roughly in this form for a single point, and then you'll actually run gradient descent towards find the answer. Okay, so this will probably be the most, when you do this, you'll probably be the most kind of challenging coding thing that you'll do in the course. It's hopefully not too hard, but if you were asked to do this in the machine learning class without having had all these lectures, it was like, oh, that was too hard. Okay, so hopefully we built up to it and this will not be too hard to do. Okay, so this is for a single data point here, right? So this is for a single data point, right? So we've only done one data point here. Now we think about, well, if we have a bunch of data points, how do we put all these together? Okay, and this is kind of worth kind of fleshing out because most, so these, what we're going to look at are these called decomposable functions. Okay, and so this is going to be when you have n greater than 1, so data points generally, okay, and you're going to write f of alpha equals to I equals 1 up to n of f of I alpha. Okay, so this is even more common than these sum of squared error kind of sort of formulations. Sum of squared error comes up all the time in data analysis because it's simple to use, and then all these other things we've been going over and over again. But it's not the only thing to use. Sometimes they say the sum of the residuals or the absolute values, or they'll add regularization terms, or they'll kind of look at some other variance that's going on here. And so, but what's quite common is that the function, the overall function we're trying to estimate is going to be a sum of loss functions corresponding with each of the data points, right? There are n data points, each contributes to the loss function in a sum, right? This corresponds if we're building a likelihood estimate and the data points were independent and we took the product and we took the log likelihood, it becomes a sum, right? If we, and if we're trying to do the central limit theorem, and there's this kind of derivation of these, these like statistical learning formulations of a lot of machine learning and data mine problems, where you're basically trying to estimate some quantity from the data, and you think of them as independent observations, and you believe that as you get more and more, they concentrate, and you should be able to get an estimate. Well, when you're taking an average, you're basically taking a sum and then you're dividing by n, but that dividing by n, the number of data points, that's a constant factor. We can just ignore that. Maybe you push that into the FI term. And again, you get back this decomposable function. Okay, so decomposable functions, right, are when you can write the total objective as the sum of each of these terms. Okay, and then you want to take, and then the question is, okay, we want to take the gradient of f, and we typically know how to do it for each of the individual functions. That's something we can calculate. And we just calculated that when this was going to be quadratic. Now, how do we put them together to run gradient descent on all of f? Okay, so let's kind of go through quickly what you can do in so like in the common example where f of I, right, of alpha equals m of alpha xi minus yi squared, right? Then what this corresponds to is f of alpha is going to be the sum of these terms, f, and this is going to be equal to the sum of the squared error between x and y and this model, right? So this is exactly the case we have, just to write this down. So the first thing, the first way of combining these together is to called batch, gradient descent. And so if you write batch gradient descent, sometimes I'll comment that at the end. What I'm calling batch gradient descent is all the data is in one batch. But so we want to calculate the derivative of f of alpha, and we know that this is actually going to be the derivative of each of these individual terms, f of I of alpha. Okay, I can decompose a function to sum, take the derivative of all the pieces, and sum them back together again. And in fact, this is actually going to be equal to I can actually push this into the partial derivatives. I can say that this is equal to d alpha j. So this is equal to the sum of I equals 1 to n of d alpha j f of I of alpha. And this is a j, so this is for 0. d of d alpha k f of I of alpha, right? So I can even push this all the way into the partial derivatives here, okay? But in general, we can remember that using this LMS update rule, which will be actually more important, LMS update, then I'm going to get that this is going to be equal to 2 times this xi minus yi, this residual. Okay, so times this function 1 xi squared. You know, if I want to go into a higher degree, right? If this was a quadratic, this will only be the first 3 terms, but could be higher degree as well, right? So I can break this down into this LMS update rule into these into the sum of these residuals times that particular data point, possibly with an expansion. Yeah. So okay. So what's the okay? So I can recover the full gradient on the data point by calculating the individual gradient on so the full gradient on the value alpha across all the data points by calculating the gradient on each of the data points and then just adding these vectors up. Okay. So the LMS update rule. Okay, yeah, so let's write this again just because this is important and we're not in a rush here. Okay, so what I want to do is have f of alpha should be equal to the sum equals I equals n. Let's just write this out in this particular case of alpha 0 plus alpha 1 xi plus alpha 2 xi squared minus yi squared. Okay, so that's this the full sum of squared errors. Okay, and I'll write this as I equals 1. This term above here will be f of I of alpha. Okay, so this term here is going to be just this f of I of alpha. Okay, and I note from the LMS update that the derivative of f of I of alpha is going to be 2 times let's say alpha 0 plus alpha 1 xi plus alpha 2 xi squared minus yi. This is a scalar times 1 xi squared, which is going to be a vector. Okay, so this was the LMS update rule, and that means I can put this back together to say that the derivative of the full f of alpha, not just on a single data point, is now going to be the sum. It's going to be 2 times alpha 0 plus alpha 1 xi plus alpha 2 xi squared minus yi. And that's a scalar times the vector 1 xi squared. Okay, so every time I run through the sum, the 2 is the same for every term, but this term is the residual. So that's the this is the residual m of alpha xi minus yi. So this yellow term is the residual, and this term is just the data point. This is just the expanded explanatory data point. Okay, so it's I've gone xi into 1 xi squared, right? So I've just expanded it out into a vector. If I have a multi-dimensional vector, I might just stick a 1 in front. If I don't want it, if I want it to go through the origin, then it's just the data point. Okay. Okay. So this means I'm able to write the full derivative, which is the main thing I need to run gradient descent, by just computing this for each xi and yi. It's always going to be of this form. It's going to be the 2 times the residual times the data point, or the expanded version of the data point. When I have quadratic loss function, it's going to look like that. Okay, so I can calculate the residual as the sum of these terms. Okay, and because each of the individual functions, because I knew, okay, I know since f of I is convex, f of I of alpha is convex, I mentioned that, then it means that the sum of a bunch of these is also going to be convex. Okay, so this means when I run gradient descent on this, it's going to converge to a single, it's going to converge to the minimum at a pretty decent rate. Okay. What I didn't say is, what you should be thinking. We talked about being convex is good, right? That's a good thing to have for writing gradient descent. But is this strongly convex? If it's strongly convex, I guarantee to converge exponentially faster, right? So I'd like it to be strongly convex. Okay. Let's see if this is going to be strongly convex. Okay, so let's look at a simpler example where I can actually draw this. Let's look at just now linear regression, right? Where now my model f of alpha of x is going to be alpha 0 plus alpha 1 xi. Okay, so this is a simpler model, and I'll show you why I'm focusing on this, because it's going to let me draw a picture, or attempt to draw a picture. Okay, so now the expanded point xi is going to be to 1 xi, right? So it's going to be its representation in space, and this is going to be an element of R2. Okay, so that's what's going to happen here. Okay, and so I somehow want to draw a picture of this. Okay, so I'm going to draw a picture here. Let me try and draw a picture in parameter space. Right, my model, this means my, right, so this also means the model f alpha is going to be alpha 0, alpha 1. It's just 2 dimensions. So I'm going to put alpha 0 on the x-axis and alpha 1 on the y-axis. Okay, and so now my function is going to live in this space. Okay, so let's try and write the function f1 alpha, which I want to look like alpha, or dot product between alpha and 1 minus and the vector 1 xi minus yi squared. Okay, right? So that's what the model function looks like. It's a dot product squared with something. And what that's going to mean is that where is this function going to be equal to 0? where is this function going to be equal to 0? It's going to be equal to 0, equals to 0 at, how do you draw an at symbol? Okay, so let me just write out the word at, that's simpler. At when alpha 1 xi is equal to yi. That's where it's going to be equal to 0. And so where's the dot product with a vector 1 xi, right? When's that going to be equal to 0? That's going to be a line. Okay, so this is where it's going to be equal to 0. This is going to be where f1 alpha equals to 0 on some line here. And you can think of this as there's some vector. The vector is actually at the origin, but it should be, this vector is going to be 1 xi, right? That's what the vector is, and basically the distance from the origin should be yi. Let me move this over so this. Okay, so there's some vector pointing in the direction here. Okay, pointing in some direction, and I want this dot product with yi to be exactly equal to 0, and so that's where if I take a data point, if I take a particular value of alpha, right, and I take the dot product with that vector, I want it to be exactly equal to yi, and so that corresponds with the line. Okay, and then what does the function look like? The function is 0 there, but it's this quadratic function. That means that this function is going to be these parabolas coming up off this line. Okay, this is a little bit harder to draw. Okay, there's these parabolas, and it's forming like a half pipe. Okay, so if any of you are skateboarders or snowboarders, and you know, like these half pipes, it's kind of like a bowl in the middle, and it's kind of like a tube with a, hopefully you know what I'm kind of drawing here. Okay, and so there's this parabolic function that's on the bottom of the line. The bottom of it has a cost of 0, and it goes up quadratically on this axis, parameterized by some line. And a different data point is going to give us a different line. Okay, so for one f of I, for one term of this function, it's not strongly convex, because along this green line in the base, on the bottom of it, it's not going to be lower bounded by this quadratic function in that dimension. Okay, so it's not strongly convex in this case. So that means for one point, I don't get the strong convexity. I don't necessarily get fast convergence here. Okay, but what happens if I draw a second line through here? Okay, let's draw another data point. So if this is the direction of 1, x2, then this is a different line, and it's going to correspond with a different sort of half pipe here. Right, there's a different half pipe that's coming through this line. That's defined by this line. Okay, and now what happens is if I just have these two functions, I'm going to get this point here, which is the true minimum. Now there's one point where both of these functions I'm adding together. Right now, f of alpha is equal to f1 of alpha plus f2 of alpha. Okay, and now they're both 0 at this black point. So that means at that point, the sum of them is also 0. But everywhere else, in at least some direction, it's growing, it's growing quadratically in all the other directions. Okay, so this is true. If I put two of these functions together, it's always going to be, it's going to be strongly convex now in this two-dimensional space. And in general, this is going to be true that this is going to be strongly convex if I stack these functions together, 1 x1 squared, 1 x2 squared, if this is going to be full rank. If I take this data matrix of these expanded points and I stack them on top of each other, and that's full rank, that means that there's not some subspace that all the data points lie on. And that's going to imply that the functions are going to be strongly convex, that there's not this kind of weird minimum where it's not growing quadratically along that direction. Okay, so and this is also required, for instance, to do a inverse on the matrix, right? To calculate the closed form solution, right? So as long as I add that term, that's also going to allow me to do an inverse, which is what I need for the closed form anyways. So if I can do that closed form solution, I'm also going to be strongly convex, and I can do a really fast gradient descent to get a really good solution that way also. Okay, so this being able to decompose these functions gives you a lot of insight into what's going on. Okay. So good. There's one more, probably even more important thing I need to tell you about these decomposable functions. So this is what about big data, right? What happens when big data, when n is very big? Okay, so this is then the problem is at this point so calculating the derivative of f at some value alpha is equal to the sum I equals 1 to n, right? This takes at least O of n time, at least linear time in the size of the data. I have to, for every data point, I have to calculate at least the residual, and I have to add up its contribution, right? Even with this least mean squares update, which makes it very easy to do, the derivative is going to be basically just calculating the residual and adding up the contribution of the data points. It's at least O of n time. O of n, or I have it right, omega of n is a lower bound, right? But n times the size of the expansion, right, of the k or d-dimensional space we're optimizing. Okay, so this can be kind of slow, and with modern data analysis machine learning, we have massive data set size. We don't want to do this, but what we learned from the concentration of measures section is that, well, this is the sum, it's kind of like an average. We can approximate it with like a sample, right? So we're not going to quite take a sample. Sometimes they call this batch update step. They'll say, we'll break the data set into batches and calculate the gradient of each batch one at a time and do that. So we're going to instead think of doing just one data point at a time. Okay. So instead, we're going to approximate this full gradient in basically constant time, right? O of 1 time, right? And we're going to do that with just the classic way of doing it is just using a single data point. Okay. Okay, so the way I can use, and again, I know f of I of alpha is going to be equal to 2 times the residual times 1 xi squared. Okay, and so then this is basically, I'm just going to use this one tool inside of what's called incremental gradient descent, okay? And so I'm going to, this is again going to be a very simple algorithm. I should be able to write it on the bottom of the screen. Hopefully it, I think it won't be too scrunched here. If not, I'll rewrite it. So I'm going to, so initialize alpha 0, right, for some initial model parameters. And I'll set I equals 1. Okay, and then I'm going to just repeat alpha k plus 1, or k is equal to 1. Okay, so k plus 1 is going to be, say, 0 here. Okay, is going to be alpha of k minus some learning rates, which might be changing if I want it to be, times the gradient at just, oh yeah, this should be I. The gradient of at data point I here, okay? So I'm going to update this. I'm also going to have k equals to 0 here, okay? And then I'm going to update I equals I plus 1, so mod n. So if I get to the end of the list, I'm just going to wrap around at the beginning, right? So if I need k steps, if k is more than n, then I just wrap around and reuse data points twice. It's not unheard of to go through a data set 2 or 3 times to do this. Maybe I've sometimes 20 or 100 times, okay? But if I go through it 3 times, that should be about as fast as 3 steps with the full gradient, right? So that should be a big win. To until, and we'll say again, the gradient f of alpha at k is going to be less than some threshold. Okay. All right. So until the gradient is small. Okay. So this step. So okay. So overall, it should look just like gradient descent, except I'm rotating through the data points in incremental order, only using the gradient defined by 1 data point at a time. Okay, maybe I make my step size, maybe I make the learning rate a little bit smaller because I don't trust the gradient as much, right? So I'm going to take a little bit smaller step because even if I'm heading in the right direction, I kind of want to take maybe 5 steps or more steps together to give me kind of the full update. As what I would do with 1 step with the full gradient, but maybe I don't need all the data points. So maybe I make some, maybe, you know, maybe make smaller than the full gradient descent. Okay, because then I'm basically averaging together a number of steps, but I'm updating the gradient as I go, right? So I'm improving my estimate every time I do that. So it should generally work maybe a little bit better. Okay, the other thing is this this in dark blue. Okay, so this check, convergence check, I might actually have my model hit one of the data points exactly, or be very close to one of the data points, but that doesn't mean I'm done, right? Because remember, the size of the gradient is now going to be proportional to the residual at that data point. And so that's not, I don't want to stop early because I hit 1 data point that models well. So I might want to take as a kind of a running or a sliding, right, as like a sliding average over, say, b steps. So I want to say if the average gradient drops below some level. Okay. So this is incremental gradient descent. I've just changed gradient descent by instead the key thing here is that I've replaced the full gradient with the gradient at one data point, right? That's the key change, right? Grade at one data point. Okay, so this is actually some version of this is actually what is most commonly used in most large machine learning frameworks within, whether it's a deep neural net or just a typical way you would actually solve a really large problem on regression. Okay, you probably would not try and aggregate everything into a matrix and then do A transpose A and take the inverse of this. You often don't want to do that. You often want to run this incremental gradient descent. And if your data set is big enough, you will actually finish before you hit all the data, right? So this might be sublinear time. You might finish before you finish reading all the data. And this is not that uncommon to happen, right? You're like, I can stop once I think the gradient is not improving anymore, right? Okay, so with this incremental gradient descent, this is typically what's used. What's typically analyzed and how this is typically referred to is called stochastic gradient descent. Okay, so this is what, when people refer to this, they usually call it stochastic gradient descent instead. This is actually a slightly different algorithm, and it basically adds some randomness into this. And this one you can actually analyze. You can do a pack-bound analysis of how well this works. This one, but it's because if you assume your data is actually IID and it's independent, then this will actually they might effectively be the same thing if your data is actually already randomly ordered. So then you just repeat. So I'm going to So I'm going to randomly choose some I in 1 up to n. So I'm going to randomly choose one of the data points. I'm going to compute my update. Right, is going to be minus the learning rate times at k. Okay, until again the average gradient, and again this is less than some threshold, and then return alpha k as my model. Okay, so this is a randomized version of this algorithm, and it's randomized because I'm going to randomly choose which coordinate to do that. Okay, if my data was randomly ordered, then these are effectively the same, and a lot of times machine learning people like to assume the data was randomly ordered because you model as IID. If you want to be careful, you might actually want to randomly order and then do incremental gradient descent, or actually do something where you choose each data point randomly every step, because there's a chance that there's a chance that you've chosen that when the data was given to you, it was pre-processed in some way, just on the order they got them, and they may have gotten them based on some process that put them out of order. And so if you learn only on the top half of that data, then you might come to the wrong conclusion with incremental gradient descent. It could so it could also happen that that if the data, if it's been ordered in some strange way, then the first half of the data will have you converge to one minimum, the second half to another one, and then you repeat back and forth, and it looks like you're always kind of moving. Whereas if you randomly do this, it should, and you average over a number of steps, it should work pretty well. So cool. So great. So that was mainly what I wanted to cover. Yeah, I'll add one more note here. There's been so recently, people have found that either so running SGD tends to generalize better than kind of full or batch gradient descent. Okay, so this is a pretty recent kind of observation. Okay, and so kind of what's happening here is that your cost function might look something like this. And so the true minimum of this cost function, this might be alpha star. Okay, but this is the result of a bunch of data. And it could be that there's actually some other, let's call this alpha prime, okay, which is a different sort of model. And so kind of so think of how unreasonable would it be that alpha prime was actually the true model here, right? So if you remember, this is made up of the sum or the average of a bunch of these individual data points. And when you have one of these, if it's this parabola like this, it could be that the height difference here is actually pretty small, right? The difference in height between these two things, kind of this delta kind of is very small. And it could be that, well, it's full rank, but in one of the parameters, it's actually fairly flat. A lot of the half pipes kind of don't care about that parameter so much. And so they're kind of flat in this direction. Actually, if I think about these half pipes, what's going on in higher dimensions is that the half pipe is actually a like the base of it is actually a d-1 dimensional subspace. Okay, so every data point leaves d-1 dimensional points, basically, a d-1 dimensional span of points. It assigns all of those with a cost of 0. And so it could be that some of the parameters aren't so meaningful, and a lot of these half pipe functions basically correspond with that. And so the difference between alpha star and alpha prime, which might be the true model, might be pretty small in height function, but might be fairly far apart. Okay, and so what's happening with gradient descent? See, gradient descent is going to go straight down here and it's going to stop. Whereas stochastic gradient descent, you might take some of these with SGD, you might take some of these smaller steps right? And you might not end up at the true minimum. Once it kind of, if I look at this region here, on average, this is looking fairly flat after a while because I'm looking at single data points and I'm averaging over a few of them. So it might stop early. It might stop away from the minimum, okay? And it tends to generalize better, it turns out, than the true minimum in a number of cases. This is often true if usually you need to either regularize the data, which means you put in some bias term, or you start the model value maybe at all zeros. And what this tends to do is if you start at all zeros, if I start at 0, 0, 0 here, right, this is alpha 0, then I'm going to, if I stop earlier, I'm going to tend to have a simpler model. The coefficients will be smaller. I'll tend to stop with the smaller coefficients. And so that tends to generalize better in some ways. Okay, so stochastic gradient descent or incremental gradient descent are actually just as easy as the full gradient descent, and they should be much faster on big data. They might be a little bit noisier in how they walk to the minimum, but that ends up tending to generalize to new data a bit so better than you would otherwise. Yeah, so I finished all the material I was hoping to cover today a little bit earlier than normal. So either we can stop the lecture here, or if you want me to go over any part of this section for what's going to be on the quiz next Monday, now's a good time to ask, and I can go over any part that you guys might have questions about. Oh, yeah, so that was an old question. I got excited. I always get a little bit excited when you ask questions, so feel free to ask them. I can go through the stuff on the collab again, so maybe I'll do that. Okay, what it means to be strongly convex. Okay. Okay, so I'll explain this in so two ways. Okay, so first I'll give you an intuitive understanding, and then I'll write down mathematically what this is again. So f of alpha is strongly convex if at each alpha in RD there exists quadratic functions Q1 and Q2, which again both go from RD to R, so that all points in some local neighborhood around alpha have Q1 P less than f of P and Q2, and which is greater than Q2 of P, and Q1 of alpha is equal to f of alpha is equal to Q2 of alpha. So, okay, so basically, if we have a function, if this is my function f, then at some point alpha, this is actually alpha here, there's going to be two functions which are going to be like parabolas. this is going to be, this is Q2, this is Q1, that are both, that one's going to be inside, one's going to be outside of F. So the Q2 function corresponds, this part has to do with the gradients is going to be L, so Lipschitz. So it means the gradient of gamma F is going to be L Lipschitz, which means that there's some quadratic term, which the gradient of Q2 effectively is going to be have a linear as a linear gradient, and so it's going to be bounded by this linear gradient function. And then this other side here, that the Q1 is lower bounding, this corresponds with when I wrote out this expanded form. Right, so let me, I think I can write this out and then get on to this other question that's appeared here. Okay, so this is, remember, I could write, I basically want Q of P to be F of alpha plus this gradient at alpha at P minus alpha, this inner product, plus some term eta 2, which was, and then this was going to be, yeah, this was P minus alpha squared, I think. Yeah, so as I move away from alpha, as P moves away from alpha, right, it should be, this is Q1, yeah. So as P moves away from alpha, it's still going to be quadratically changing, right? That's what this last term is saying. And the first two terms, right, these two terms allow me so that I'm not just talking about the minimum. Otherwise, I'm only talking about the minimum. It allows me to shift this discussion where I've added this linear component and the offset component. So that's what those terms are doing. Otherwise, this is just a parabola. Okay, and so I'm saying lower bounding by parabola. And when I have this means, turns out totally parabolic functions, gradient descent works super fast. And this means that any function that satisfies this will work super fast, even if it's not just some parabola plus linear and constant terms. Okay, so hopefully that explains what these strongly convex functions are about. And this allows me to say, after every step, I'm basically resolving 1 bit of precision, roughly, which means that exponentially fast, I'm figuring out the right answer. Okay. Okay, so what do can you explain what differentiates a decomposable function from other functions? Okay, so again, a decomposable function is going to be of the form f of alpha equals 1 to n of f of I of alpha. And the idea is that each of these is going to have a kind of a simple form. I'll be able to understand what's going on with each of these individual terms, and then I can just add them up. And this has the power that I can decompose the gradient into this batch approach, or I can do stochastic gradient descent or incremental gradient descent that I can't do generally otherwise. An example of a non-decomposable function would be something like f of alpha equals to, let's say, alpha 1 plus 1 plus alpha 2 times alpha 3 squared times alpha 1 minus alpha 2 times alpha 3 squared, right? So something like this, right? I could probably expand. This is a polynomial of three, of three variables. I could probably expand it into these terms of this polynomial, and then I could say that it's kind of decomposable in that way, but that's kind of not the general purpose. I mean, that's effectively how you will be taking the gradient of if you get a function like this. You would probably, what I would do is I'd probably expand it into a single so monomial, and then just use simple polynomial derivatives. That's pretty easy to do. But the point is, in a decomposable function, usually each fi corresponds with, it comes from one data point, right? So I usually have that, I have a total loss function, f, that I want to minimize, and it's usually come by the sum of a bunch of individual loss functions summed up from a bunch of these data points. And this just shows up through lots of most of data analysis, basically the premise of building models from data. And so the decomposable functions have this, and that allows, it makes stochastic gradient descent to make sense. Whereas if this non-decomposable polynomial, I could decompose it into these terms, and then maybe I could run stochastic gradient descent on those individual components. I'm not sure that would necessarily make sense to do. They aren't intuitively like independent of each other, which is kind of underlies this why you think stochastic gradient descent should work, because these should be kind of independent terms that are all kind of being added together to represent the full data set or some underlying function that it's drawn from. So that's really what kind of intuitively distinguishes decomposable from one of these other things. So great. So I think we'll kind of stop there, but I'll at least turn off the recording. But I'm around for office hours, and so don't forget that the quiz is going to be on Monday on this